Good evening, everyone, and thank you for being with us in our third talk in a series we're calling Higher Meanings, Exploring Connections Between Religion and Mathematics. I'm Rabbi Ben Zeidman from Temple Mount Sinai in El Paso, Texas, and we're so thrilled to have you with us this evening as we join together to learn with Dr. Victor Katz. Our series of talks is a part of a national program called Scientists in Synagogues, which is a grassroots initiative run by Sinai and Synapses. That organization is supported by CLAL, the National Jewish Center for Learning and Leadership. And this program and this opportunity is brought together in consultation with the Dialogue on Science, Ethics, and Religion program of the American Association for the Advancement of Science. It is funded by the John Templeton Foundation, along with other donors. We also want to just give a very, very grateful expression of thanks to University of Texas of El Paso, and in particular, the Religious Studies program, the Computer Science Department, and the Mathematical Sciences Department here at our local university as part of the University of Texas at El Paso. We've had a lot of support from them and are grateful to them. We are going to be, as you hopefully have heard, recording this session for later viewing. I have no doubt you'll want to watch it again and again, but hopefully you'll also take the opportunity to share it with people who might be interested, but were not able to attend. We'd like to encourage you to ask questions as they come to mind. Please remain muted and insert your questions by typing into the chat. The questions that you pose will be moderated at the end by Dr. Larry Lesser, who's a professor of mathematics here at University of Texas at El Paso, and who happens to also be our first speaker in the series, Higher Meanings. We also are, I'm really glad that I have this because we're going to activate the live transcript option, and hopefully that is not too distracting. If you're distracted by the captions that are going to be automatically scrolling at the bottom, you can click where it says live transcript once that shows up and select to hide subtitle. But hopefully this creates a more engaging opportunity for those who may miss something or who can't hear as well. And then we're also going to ask you to do two things as a follow-up to this talk this evening. One is to fill out an anonymous Google Forms survey so that we can reflect on the broad scope of our various talks. And I'm also going to invite you to go to our website, and I'll put that in the chat later as well, to sign up for our next talks. This is the third in a series, a year-long series that we're holding. As I mentioned, it began with Dr. Larry Lesser, who's with us moderating the Q&A this evening. We were thrilled to be joined by Dr. Kim Jungarius last time in April. And we're looking forward to our next talk, which is Thursday, August 16th at 6:30 p.m. Mountain Time, same time, with Dr. Olga Kosheleva and Dr. Vlada Krinovich. In October, we'll be welcoming Dr. Snezana Lawrence, and in December, we'll be welcoming Dr. David Novick. To introduce Dr. Victor Katz. Dr. Victor J. Katz is a professor of mathematics emeritus at the University of the District of Columbia. He has long been interested in the history of mathematics and its use in teaching. He is the author of a well-regarded college textbook, A History of Mathematics, an Introduction, and also a book on the history of algebra titled Taming the Unknown with Karen Parshall. He is the editor of two source books, The Mathematics of Egypt, Mesopotamia, China, India, and Islam, a source book, and source book in the mathematics of medieval Europe and North Africa, with the latter including extensive material on medieval Hebrew mathematics. He is the founding editor of Convergence, the Mathematical Association of America's online journal on the history of mathematics and its use in teaching. He has been married for over 50 years to Dr. Phyllis Katz, a specialist in science education outside of schools, and has 3 grown children and 8 grandchildren. Dr. Victor Katz, thank you so much for being with us this evening, and we are so thrilled to have the opportunity to learn with you.
Okay, let me see if I can do this. Okay, well, first I want to thank Rabbi Zeidman and Dr. Lesser for inviting me to participate in this series. And I want to thank all of you for giving up a part of your evening to listen to a talk about the medieval period. So first, given that this is a talk about medieval history, I want to ask you what image comes to mind when you think of the Middle Ages. Wait, oh, wait a second. I think I didn't do something right. The slideshow is not working. Okay, why not? Just a second. Let's try this again. Okay, so what image do you have of the Middle Ages? Is it that? I asked one of my granddaughter the other day what she thought of when I think of the word Middle Ages, and she said, yeah, knights in armor. But maybe there's other images you might know. Here's an image of two Muslims discussing some point in philosophy. And that was certainly something that would happened in the Middle Ages. And here is an image of a Jewish trader. He even has a symbol on his cloak that indicates that he's Jewish, because in a lot of places Jews had to wear identifying symbols. Muslims and Jews generally didn't participate in medieval battles like the previous slide. Much of what they did was intellectual, as we will see. So what I want to talk about tonight is the way religious cultures affected, in particular, the study of mathematics. We will see that although there were religious objections to the study of science in general, and mathematics in particular, still many religious leaders claimed that God required you to learn about the world. Why? Well, there were several reasons. There was this general idea of fairness, how you figured this out. Also, to determine inheritances, especially when there are lots of kids, you certainly needed mathematics. Even more important was creating a calendar, which was very important for the Muslims and Jews early on, and later for Catholics as well. Prayer practices were also often determined by a detailed knowledge of astronomy, which in turn required mathematics. And certainly, if you were going to debate someone on any subject at all, you needed to be able to understand and produce logical arguments. Mathematics was central to doing this. Finally, we will see that mathematicians working in these three religious cultures learn from each other. All right, I'm going to begin by looking at a problem that shows up in medieval times in many places. It's called three men buying a horse. So three men want to buy a horse in common. The first says to the others that if they give him 1/3 of their money, then with the money he already has, he can buy the horse. The second says to the first and the third that if they give him 1/4 of their money, he can buy the horse. And the third says to the first and second that if they give him 1/5 of their money, then he can buy the horse. So how much does each man have to begin with, and how much does the horse cost? Well, I guess the three men must have known each other rather well so they could figure out how to share a horse. In any case, I'm not going to ask you to solve this problem right now, but if you feel impelled to do it, go right ahead. But why are we interested in this problem? Because it appears in mathematical textbooks coming from medieval Islam, from medieval Jewish writing, and also from medieval Catholic writing. Why were all three civilizations interested in a problem like this? It's hard to say specifically, but people who wrote mathematics in all three groups were interested in solving problems and in teaching students how to solve problems. Somehow this problem caught the fancy of medieval mathematicians. That it appears in texts of all three cultures certainly gives some indication that mathematicians learned from each other. The problems were in all likelihood not invented from scratch by the various authors. Also, it turns out, although the problems were the same, the authors' methods of solution were not. As we will see, this tells us something about how Muslim, Jewish, and Catholic mathematicians approached mathematics. Okay, now before we go further with the mathematics, let me remind you of some history. Remember that Islam began in Arabia in the middle of the 7th century, but was soon spread by Muslim armies throughout the Middle East, then east as far as India and west through North Africa into Iberia, which was conquered in the 2nd decade of the 8th century. Initially, the Muslim Empire was ruled from Damascus, but after many wars, the caliphate split up. In the eastern segment, here you can see a picture of this. In the eastern segment, the Abbasid caliphs founded a new capital in Baghdad, where a new culture developed. It was there that Harun al-Rashid established a library in Baghdad in which manuscripts, especially scientific and mathematical ones, were brought from Greece, India, and elsewhere and translated into Arabic. This was the beginning of a very strong scientific movement in Islam, in which scholars not only read the old sources, but also mastered them and continued to do research and make new discoveries. Now, in Iberia, which is way on the left of this map, I'll put it up again, a similar golden age began under rulers from the Umayyad dynasty beginning in 912. But after 1031, Al-Andalus broke up into many small Islamic kingdoms, as you can see on this slide, some of which encouraged the study of science while others did not. Meanwhile, of course, the Catholic Reconquista was well underway. The Catholics pushed down from the north and gradually pushed the Muslims out of Spain, as you probably remember. A critical date was 1085 with the reconquest of Toledo, which was right in the middle of Spain. Toledo had been one of the richest of the Islamic kingdoms, but was conquered in that year by Alfonso VI of Castile. Fortunately, Alfonso was happy to leave intact the intellectual riches that had accumulated in the city. And so in the following century, Toledo became the center of the massive transfer of intellectual property undertaken by the translators of Arabic material, including previously translated Greek material into Latin. More on that a little bit later. But what of the Jews? Well, although there were Jews in many parts of the Islamic world, it was mainly in Spain and Provence the Jews became active in mathematics starting in the 12th century. During the 11th century, with the breakup of Al-Andalus and the return of Catholic rule to parts of the peninsula, Jews were often forced to make choices of where to live. Some of the small Islamic kingdoms welcomed Jews, while others were not so friendly. The Catholic monarchs at the time often welcomed Jews because they provided a literate and numerate class, fluent in Arabic, who could help the emerging Spanish kingdoms prosper. So by the middle of the 12th century, most Jews in Spain lived under Catholic rule. But once the Catholic kingdoms were well established, the Jews were often persecuted. So that in the 13th century, Jews started to leave Spain, with the final blow coming in 1492. By then, many Jews had moved to Provence or to Italy, and it was there that Jews began to fully develop their interest in science and mathematics. They also began to write in Hebrew rather than in Arabic, which was their intellectual language back in Muslim Spain. Now, in this talk, we're going to concentrate initially on Muslim and Jewish work in mathematics, since the Catholic work generally came much later. And we will break this study down into various topics of mathematics. So we're going to start with arithmetic. Now, as you probably know, well, first of all, arithmetic was necessary for everyone. Anybody who had to be in the marketplace had to do arithmetic. But what do we mean by arithmetic? Well, calculation to start with. And after all, our base 10 place value system comes from India, but it was transmitted to Baghdad in the 8th century. And it turned out, you know, you might think that because this system was very useful, that it would easily replace earlier systems that Islamic people had. But it wasn't quite so simple. One problem with this medium was that calculations were generally, at the beginning, were generally done on a dustboard, a board covered with sand on which the tradesmen wrote the figures. But one Muslim scholar wrote, "Many a man hates to show the dustboard in his hand when he needs to use this art of calculation for fear of misunderstanding, since it is seen in the hands of the good-for-nothings earning their living by astrology in the streets." So people didn't necessarily want to use it. Muslims actually often use finger reckoning. Now, this slide is not Muslim finger reckoning. This comes from Europe, but because we don't know exactly how the Muslims used finger reckoning, but it was probably a system similar to this. But finally, with the fortunate introduction of paper, in the Islamic domains, they eventually adopted the base 10 place value system and started to write books on how to use it for calculation, how to do various algorithms. The Jews, like the Muslims early on, usually used the letters of the alphabet to represent numbers and did calculations on some kind of counting board. But by the 12th century, they had adopted the Hindu system, but instead of using the numbers that we're used to, they used Hebrew letters for the first 9 digits. You can see in this circle here, and they used a circle for 0. They also learned the appropriate algorithms to do calculation. And although arithmetic was certainly necessary in various aspects of daily life, it was Abraham Barchia, a Spanish Jewish scholar from the early 12th century, who wrote about its religious importance, in particular for calculations regarding the Jubilee. Now, I don't know if you remember what the Jubilee is, but here's a quote from Leviticus 25, where it's talked about. You shall count 7 weeks of years, 7 times 7 years. So the time of the 7 weeks of years shall be to you 49 years. Then you shall send abroad the loud trumpet on the 10th day of the 7th month, and you shall hallow the 50th year and proclaim liberty throughout the land to all its inhabitants. It shall be a jubilee for you, when each of you shall return to his property and each of you shall return to his family. What that meant was that all debts were released and people had to give back land that they had bought and all sorts of things like that. And so what Abraham wrote was, the scriptures say, I, the Lord, am your God, instructing you for your own benefit, guiding you in the way you should go, from which you learn that any craft and branch of wisdom that benefit man in worldly and holy matters are worthy of being studied and practiced. I have seen that arithmetic and geometry are such branches of wisdom and are useful for many tasks involved in the laws and commandments of the Torah. We found many scriptures that require them, such as, in buying from your neighbor, you shall deduct only for the number of years since the Jubilee. And the more such years, the higher the price you pay. The fewer such years, the lower the price. Followed by, do not wrong one another, but fear your God. So, no, as he further said, no man can calculate precisely without falsification unless he learns arithmetic. So there was a religious reason for learning arithmetic. But what other reasons do you need to study arithmetic? Well, Abraham ibn Ezra, who was born in Spain and later traveled widely during his lifetime, wrote a good deal about mathematics. He talked about the study of proportions, right? Here's a problem in proportions. Fairly simple. Reuben hired Simon to carry on his beast of burden 13 measures of wheat over 17 miles for a payment of 19 pashoots. But he carried 7 measures over 11 miles. How much should he be paid? All right, you needed some methods of calculation to figure this out. Also, Abraham was an early contributor to combinatorics, ways of counting various sets. In particular, he believed that when 2 or more planets had a conjunction, that is, when they appeared together in the sky, this was an important portent of events to happen on the Earth. Thus, he used his skill in calculating to develop the basic method of determining how many possible conjunctions there could be of the 7 wandering heavenly bodies. Remember what they were in his day: Mercury, Venus, Mars, Jupiter, and Saturn, and the sun and the moon. Those were the wanderers in the sky. Now, Muslims and Jews contributed further to this study over the next couple of centuries. Interestingly, the major question for both groups ultimately was not conjunctions, but how many words could be formed out of the letters of the alphabet, either the Arabic alphabet or the Hebrew alphabet. For Jews, this was a religious question, since they believed that God had created the world and everything in it by naming these things. In Hebrew, of course, which was God's first language. So the question was, how many things could be named? That means how many words can you form? By 1321, Levi ben Gershon, who we will talk about a little later in more detail, had rigorously calculated the basic combinatorial formulas based on earlier work by Islamic mathematicians. All right, now, growing out of arithmetic, beginning in the 9th century, was the science of algebra. The first algebra text was written around 825 by Muhammad al-Khwarizmi in Baghdad. Now, Muhammad al-Khwarizmi, his name al-Khwarizmi means he came from Khwarizm, which is now in Western Uzbekistan. And if you go to Urgench in Uzbekistan, you'll see the statue of Muhammad there. Of course, there's no picture of Muhammad, but somebody just created this statue. Doesn't mean he looked like that. In any case, he wrote this first algebra text around 825. As he said in the introduction, that fondness for science by which God has distinguished the Imam al-Mamun, the commander of the faithful, has encouraged me to compose a short work on calculating by Algebra and al-Muqabala, confining it to what is easiest and most useful in arithmetic, such as men constantly require in cases of inheritance, legacies, partition, lawsuits, and trade. Okay, so what he says was the study of algebra was to be able to solve questions of inheritance, partition, lawsuits, trade, etc. However, the central part of al-Khwarizmi's algebra text was the presentation of the ways of solving quadratic equations. Now, I'm sure you all remember how to solve quadratic equations. You got this drummed into you when you studied algebra back in 9th grade, or maybe earlier. And you may remember from your algebra texts that any word problem about quadratic equations was quite artificial. The textbook authors who wrote your textbooks could never figure out exactly what kind of problems, real world problems, needed quadratic equations. And neither did al-Khwarizmi. His book has a large number of problems dealing with inheritance, because he said that's important. But those problems don't need quadratic equations to be solved. Generally only linear equations. And all the quadratic equations he had in there were abstract, with a very few word problems that were sort of very fake. So it's really interesting that al-Khwarizmi was trying to justify the study of quadratic equations, but actually that subject was not necessary for everyday life. Although Islamic mathematicians continued to write algebra texts over the next several centuries and made many discoveries of a rather advanced nature, none of these mathematicians could actually point to real life problems that required quadratic equations, only to interesting theoretical questions. Because of this lack of application, the Jews generally didn't study the subject. Here's a quotation from a Jewish philosopher in Toledo in the middle of the 12th century. As he says, among those who spend their time on vanities, thereby depriving their soul of the afterlife, is he who consumes his time with number and with strange stories like the following. A man wanted to boil 15 quarters of new wine so that it be reduced to a third. He boiled it until a quarter thereof departed, whereupon 2 quarters of the remaining wine were spilled. He again boiled it until a quarter vanished in the fire, whereupon 2 quarters of the rest were spilled. What is the proportion between the quantity obtained and the quantity sought? So again, Abraham was sort of pointing out these kind of ridiculous problems that were in algebra texts at the time and saying, why do you need to do this? Now, so Jews didn't study algebra. In fact, many Jewish authorities at the time wrote that Jews should limit their studies to the Torah and the Talmud. But the most important Jewish philosopher of the Middle Ages, namely Maimonides, who lived from 1138 to 1204, at first in Spain and later in Egypt, convinced Jews that they in fact should study mathematics. As he wrote, the study of science and philosophy was actually a religious obligation, beginning with logic. Maimonides emphasized that it was only truth that counted and that it did not matter who discovered it. On the other hand, since it was the divine science of metaphysics that was the ultimate goal, Maimonides emphasized that science was legitimate and desirable only insofar as it contributed to the divine science. Thus, medieval Jews were to study mathematics either because they prepared the intellect to apprehend abstract truths or because they needed it as a prerequisite for the study of mathematical astronomy. But for Maimonides, algebra was a mere technique, having no philosophical value or even practical use. Now, this picture of Maimonides, again, is traditional, although we have no idea what Maimonides actually looked like. But it turns out the signature at the bottom is his actual signature. That was discovered in the Geniza in Cairo. Okay, so let's move on to geometry. Going back to Abraham Barchia. Well, first of all, there's two parts of geometry that were of interest. I mean, anybody who knew something about geometry knew that Euclid had written this major work, The Elements of Geometry, but it was an abstract work and used logical proof from explicit axioms. But people were also interested in other kinds of geometry, practical geometry that was actually necessary in one's life, including the calculation of areas and volumes. So Abraham Barchia wrote as follows: geometry is useful for following commandments from the Torah, but is difficult to understand, so one has to study and interpret it for land measurement and division between heirs and partners. So much so that no one can measure and divide land rightfully and truthfully unless they depend on this wisdom. I have seen that most contemporary scholars in Spain and Provence are not skillful in measuring land and do not divide it cleverly. Their calculation might mete out a quarter to the owner of a third and a third to the owner of a quarter, and there is no greater theft and falsification. So Abraham himself, and he wrote his treatise on geometry, he presented not only rules for finding areas and volumes, but also presented methods for dividing land, including what one should do when land is on a slope. Abraham ibn Ezra also wrote a good deal about practical geometry. As to theoretical geometry, even Maimonides felt that its study was useful. After all, Euclidean geometry is itself a major exercise in logic and was therefore important in being able to understand abstract truths, important for the study of metaphysics. Interestingly, Maimonides explicitly cites the study of conics, that is, parabolas, ellipses, and hyperbolas. Those of you who know something about mathematics know something about these, that this was a topic that is commendable only in as much as it follows the aim of sharpening the intellect and getting the intellect used to demonstrations, which is the way through which man achieves the knowledge of the true existence of God. Now, Maimonides believed that part of the study of conics was useful in sharpening the intellect. In particular, he believed that the existence of asymptotes showed that just because you could not imagine something did not mean that it did not exist. And what he meant by that, he wrote, you know, it has been made clear in the second book of the conic sections, that was this treatise by Apollonius, that two lines between which there is a certain distance at the outset may go forth in such a way that the farther they go, this distance diminishes and they come nearer to one another, but without it ever being possible for them to meet, even if they are drawn forth to infinity. And even though they come nearer to one another, the farther they go. As he said, this cannot be imagined and can in no way enter within the net of imagination. Of these two lines, one is straight and the other curved. So he was impressed by this, and as he said, hear what the mathematical sciences have taught us and how capital are the premises we obtained from them. Okay, now I mentioned Levi ben Gershon, who was the foremost Jewish mathematician of the Middle Ages. On the left here is a slide of Rehov Ralbag. This is a street sign in Tel Aviv. And those of you who have been to Tel Aviv probably know that most of the streets in Tel Aviv are named after people. And at one end of the street or the other, there's a little blurb about this person. And here it basically says that Levi ben Gershon was a philosopher, a mathematician, an astronomer, and a biblical commentator. This is, those of you who have been to Tel Aviv probably have not run into this street. It's a street in the south of Tel Aviv, and it's not in a very nice neighborhood, but I went and found it a couple of years ago when I was there. Okay. Levi certainly had read Maimonides' works. Everybody had read Maimonides, but he interpreted Maimonides differently from most others. Namely, he felt there should be no restriction at all on what one could write about in science or mathematics. Because all knowledge of God's works has religious significance, the acquisition of scientific knowledge about the world is a legitimate end in itself. So Levi explored many different aspects of science and mathematics: combinatorics, geometry, astronomy, and even number theory. In his work, he had first consistent use of the technique of mathematical induction. Now, I won't explain it to those of you who don't know what mathematical induction is, but all the mathematicians in the audience certainly know what it is. And he was the first one that used it very, very consistently in proving a number of results in combinatorics. But then he wrote this treatise on number theory that he wrote at the request of a French music theorist. So he was in contact with non-Jews, certainly. He proved the theorem that a power of 2 must differ from a power of 3 by at least 2, except for the 4 pairs that are written there: 1, 2, 2, 3, 3, 4, and 8, 9. And this had to do with production of tones in music. You know, these 4 pairs of numbers are, if you set these up as lengths of strings, the ratio of lengths of strings, you know that 1 to 2 gives you an octave, 2 to 3 gives you a fifth, 3 to 4 gives you a fourth, and 8 to 9 is a single tone in the normal scale. Okay, there were other mathematicians in Spain and France who also ignored Maimonides' strictures. The most important was perhaps Abner of Burgos, who lived from 1270 to 1348. He wrote a text whose aim was somehow to show that there exists a rectilinear area equal to a circular area, exactly, not just approximately. But in the only manuscript we have, the concluding chapter where this was to be accomplished is missing. Still, one of the chapters has many interesting mathematical discussions, including a study of the use of this curve. It's called the conchoid of Nicomedes. And again, I'm not going to discuss it, the details of it, but this curve had first been used in ancient Greece. But until the work of Abner was discovered in the last 30 or 40 years, nobody had talked about the conchoid of Nicomedes until the 17th century, or it was thought that nobody had talked about it until the 17th century. But Abner showed how to use the curve to solve 2 very famous old Greek problems: how to trisect an angle and how to double a cube. Now, the Muslims also studied geometry. They fully absorbed the Greek notion of logical proof from axioms that came from Greece. And they carried the ideas of theoretical geometry well beyond Euclid. They also did a lot of work in practical geometry of the sort that I mentioned earlier, areas and volumes and things like that. Now, usually for the Muslims, there wasn't any religious restriction to studying geometry, but there was always in Islam a countercurrent among certain Islamic authorities that although they acknowledged that the basics of the ancient sciences, such as mathematics, were important for the Islamic community, they believed that overstudy of these sciences could lead to conceit and a falling away from the faith. And this conflict continued through Islam for centuries, even though Muslim scientists were often engaged in wonderful original work. And as time went on, Islamic authorities clamped down more and more on doing things outside of the study of religion. All right, let's move on to astronomy. Now, this was certainly important for Muslims and Jews. In particular, Muslims needed to understand astronomy so they could determine the direction of and the correct times for prayer. Jews needed astronomy to help them work out the intricacies of the calendar. Now, the main mathematical tool for astronomy was trigonometry, the study of angles and lines and triangles. And although plane trigonometry was useful, it was spherical trigonometry that was the basic tool for studying astronomy, because the Earth was a sphere and the heavenly bodies moved on the surface of the heavenly sphere. And this is just a diagram of a spherical triangle, so you see what we're talking about. Now, for Muslims, one of the religious challenges was determining the direction of Mecca, because that was the direction in which one prayed. Now, by the direction of Mecca, Muslims meant the direction along a great circle that connected your location with Mecca. Now, remember, a great circle on the Earth is a curve. It's in the left picture here, such that a plane passing through it goes through the center of the Earth. In general, a great circle route is the shortest distance between 2 points on the surface of the Earth. It's the curve generally followed today by an airliner on a long flight. I mean, and this is just an example, going from somewhere in the eastern United States to India. You fly well north and then come back south again, but that's the shortest distance. But it was never a trivial problem to determine the correct great circle, even if you knew your geographical coordinates. And of course, you had to know the geographical coordinates of Mecca. Many Muslim mathematicians worked on this problem for years to find various methods of solution. In the process, they developed spherical and also plane trigonometry far beyond the version they had inherited from the Greeks. Now, as it turned out, if you go look at mosques around the world, not all Muslims were willing to go through the mathematics necessary to correctly align a mosque. So many mosques were situated with a direction of prayer just approximately toward Mecca. But there were a good number of them where we have records of them doing this quite difficult calculation. But also, astronomical knowledge was necessary for determining the right times of day to pray. Muslims were supposed to pray 5 times a day, and this depended on when the sun rose and set, among other events. Now, you may also know that Jews wanted to pray toward Jerusalem. Before we really go to this slide, I just want to mention, when the tradition developed that most Jews lived in European countries, generally west of Jerusalem, so they oriented their synagogues toward the east. But they didn't actually try to calculate the direction of a great circle. They didn't do what the Muslims did. They simply decided they should pray toward the east, and therefore made clear in the synagogue which wall was the eastern wall. Thus, praying toward the east became a tradition, even though, if you look at a map, you can see that if you were living in the Ukraine, the direction of Jerusalem is south. Nevertheless, the eastern wall was the direction that you prayed toward. Okay, on the other hand, you didn't need trigonometry for the astronomical knowledge to correctly determine the calendar. What did you need to determine the Jewish calendar? Well, all sorts of things. The time when Shabbat began or ended, the day when the new month began, the time when the holidays began, the times of prayer, and so on. Abraham Bar Chia and Maimonides himself wrote detailed treatises on the calendar. And Levi ben Gershon wrote a trigonometry text, which formed the basis of some of his astronomical work that was used by others for the religious purposes I just mentioned. Now, Levi was without doubt the most accomplished Jewish mathematician of the Middle Ages. Even though he went beyond the standard interpretation of Maimonides in deciding that he could study and write on any topic he thought interesting, he had few followers. There was a conflict within the Jewish community regarding what subject could legitimately be studied. And as I said earlier, there were a sizable proportion of traditionalists who disagreed even with Maimonides and insisted that only the Torah and the Talmud were worthy of study. But a further issue for the Jews was that there was no institutional infrastructure in which students could learn mathematics. One could always arrange to study privately with an individual, but there were no Jewish universities, and there were no Muslim universities. And to find a particular private teacher was not always easy. For the Muslims, there was the same issue. They did have madrasas, these very famous schools, and And this is a slide. This slide is this big square in Samarkand where there are the two buildings on the left and the right are old madrasas. But in the madrasas, they were generally studying only the religious sciences. Occasionally, Muslims could teach scientific subjects there, but most of the time, as in the later Middle Ages, Muslim religious orthodoxy more and more prevented this. So there were no good universities where Muslims could study. As a Muslim cleric wrote, study of certain aspects of the mathematical sciences require their practitioners to direct themselves to beings other than God. And this was to be avoided. Now, a Jewish doctor around 1400, Leon Joseph of Carcassonne, wrote about this very issue. He complained that Jews generally lack knowledge of the secular sciences because science is as far from the fundamentals of the Torah and religious faith as East is from West. And furthermore, what he said, those few who did study the sciences had no right to propound their knowledge in the squares and in the streets, or to discuss it, or to show themselves favorable toward it, or to conduct public debates with the aim of reaching the complete truth. For knowledge of the truth can only be attained by means of the contrary. So Leon decided to study Latin and attend secular universities. He found that the way of studying that they practiced today at his day in the Catholic universities was basically the same as Jews had used to practice in studying the Torah, by disputation, by argument. But Jews weren't allowed to study mathematics or the sciences in general. He noted that the Christians have continued to advance in the secular sciences, while we Jews have continued to lose ground as a consequence of distress and oppression. Now I'm going to talk about the Catholics because, in fact, it was the existence of universities in Catholic Europe beginning in the 12th century, along with a concurrent flood of translations from the Arabic, that provided the impetus for the study and practice of mathematics and other sciences in Europe from that time on. These translations, as I said earlier, were mainly in Spain, to begin with anyway. They included Greek material that had been preserved in Arabic, as well as much more contemporary Islamic work, and even some work originally written in Hebrew. In many cases, a particular manuscript was first translated by a Jew from Arabic into Spanish, since Jews were familiar with both languages. It was then translated by a Catholic translator from Spanish into Latin, so that it would be useful throughout Europe. It was only after this translation activity took place that Latin Christendom began to develop its own scientific and mathematical capabilities. Now, in mathematics, we know from the existence of Latin translations that Catholics especially learned arithmetic and aspects of algebra from the Muslims. They learned some combinatorics from the Jews and some geometry and trigonometry from both groups. In the work of Fibonacci, officially his name is Leonardo of Pisa, but he's usually known as Fibonacci. Early in the 13th century, we can actually trace the influences of Arabic and Hebrew works in both of his major works, the Libra Bacci, which means the book of calculation, and the De Practica Geometrie, on practical geometry. A lot of material in there came from Muslim and Hebrew sources, and we can pretty much see where they came from because the Muslims and the Hebrew sources are still available to us. On the other hand, if we look at other Latin mathematical writing in the Middle Ages, we sort of can assume that Catholic mathematicians became aware of other work, whether through personal contact, translations that have not yet surfaced, or maybe just verbal transmission. There are often such great similarities between early European Latin mathematical works in trigonometry, combinatorics, geometry, and algebra, and work that was originally in Arabic or Hebrew, that it is difficult to believe that the Latin writers began from scratch. But there was no tradition in those days to put in footnotes and say you got this material from someone or some set of people. You just wrote. I want to look at two particular examples of this. I mentioned that Levi ben Gershon had worked out in detail the basic combinatorial formulas. He had worked in 1321 in his work Ma'aseh Choshev. Okay, these are the two formulas. I don't want to discuss them. Those of you who know the mathematics have seen these formulas many times. These are the ways, number of combinations of n things taken r at a time, the number of permutations of n things taken r at a time. Now, this book, the Ma'aseh Choshev, was relatively popular for a medieval manuscript because, and we know that because there's still a dozen manuscripts of this that are still in existence. So evidently some people were interested in the work. But there is nothing written about these formulas in Europe again until some works of Marin Mersenne in Paris in the 1630s. What happened to the ideas? We don't really know. Mersenne's methodology bears some resemblance to Levi's work. So did Mersenne somehow learn of this from Levi's manuscript? Well, we know that Levi's work was available in Paris. There was a manuscript in Paris. We know that it was there since 1620, and that's still in Paris. It's in the major library in Paris. And certainly Mersenne knew Hebrew. Lots of priests in those days had to study Hebrew, so they were familiar with it. So did Mersenne learn from Levi? We have no idea. Was there an intermediary who he learned it from? We don't know. The manuscript itself is interesting, has no notes on it, so we don't even know anybody who read it. But it's just a question. But a more interesting question is the following. The so-called Tusi couple. This idea occurred in Muslim and Jewish texts and later moved to Latin. Okay, the Tusi couple is a mathematical device invented in Moraga, Persia by Nasser al-Din al-Tusi in the mid-13th century to help explain some of the motions of the heavens in the long accepted proposition that the earth was the center of the universe. Now, what this diagram shows you is that straight line motion can come from a combination of circular motions. That's the basic idea here. You have these two circular motions, and you get a straight line. And from Greek times on, it was believed that all motion in the heavens was basically circular. And what you saw in the heavens, you had to figure out how circles would give you exactly what you saw. Okay. Now, as you are aware, of course, Copernicus turned this system of this Earth-centric system on its head in the 16th century by asserting that, in fact, the Earth moved around the sun. But one of the important mathematical ideas that provided the basis for his theory was, in fact, this very device, this Tusi couple. And there have been many speculations as to how he learned of it. Maybe it was during his studies in Italy, because he studied in Italy as a young man. But in recent years, however, historians have become aware that the Tusi couple appears in this work of Abner of Burgos that I was talking about earlier. Now, Abner's work was written in Hebrew in Spain early in the 14th century. The manuscript we have today was at one time owned by Mordechai Finzi, who was a Jew of Mantua in Italy. He lived in the 15th century, and we know that he had numerous contacts with Christian scholars. We don't know if Alfonso's work or any piece of it was ever translated into Latin, but it's certainly a strange coincidence that this idea that's central to Copernicus's work comes from Persia, appears in Spain, then in Italy, and finally shows up in 1543 in Copernicus's magnum opus, the De Revolutionibus, written in what is now Poland. Okay, these are just speculations, these last two slides. I can't prove anything about these, and I don't know if anybody will ever be able to, but interesting questions. Now, most of the newly translated material from Arabic was used in the mathematical part of the university curriculum. The centerpiece of the university curriculum, though, was the study of logic. And the primary texts for this were the logical works of Aristotle, all of which were also provided by the translators. Gradually, other works of Aristotle were added to the curriculum. Again, this is a traditional bust of Aristotle. We have no idea what Aristotle looked like. Maybe this was Plato, maybe this is Euclid, maybe this is someone else. But this is sort of traditional Aristotle. Often the mathematics studied in the universities was material that was studied primarily as it related to Aristotle's work in logic or in the physical sciences. Aristotle didn't have much actual mathematics, but he had some ideas about mathematics in his works, and people tried to put some mathematics into it to try to see if it made sense mathematically. Now, Aristotle's philosophy posed a problem for Catholic theologians. From Aristotle's point of view, the world was eternal. It had always existed and would continue to exist. But for Catholics, as for Muslims and Jews also, the world had been created by God out of nothing. In fact, in 1277, the Bishop of Paris drew up a list of 219 errors, which he alleged that some scholars of arts at Paris were transgressing the limits of their own faculty. In particular, he wrote that it was an error to doubt God's omnipotence, that in fact God had absolute power to do whatever he wills, including creating the world out of nothing. Thus, he condemned those ideas that could not be maintained in light of the revealed truth of the Catholic religion. But this condemnation was too little and too late. In fact, a new canon law had already been developed in the 12th century saying that anyone ought to learn secular knowledge, not just for pleasure, but for instruction, in order that what is found therein may be turned to the use of sacred learning. In essence, the study of the natural sciences and the pursuit of philosophical truth had become institutionalized in the universities, and nothing would disturb this state of affairs. The universities were not under church control, but usually had royal charters. So mathematicians and other scientists in Catholic Europe were free to study whatever they wished. In particular, one group of mathematicians who worked at a university were the so-called Oxford calculators of the 14th century. They were associated with Merton College in Oxford. Because they were involved in university teaching, they had to figure out how to explain difficult concepts to students, with, as I said before, the basic method of teaching being disputations with participation from both teachers and students. Thus, they concentrated on logical argument based on Aristotle's principles, and then used the argument to try to determine what Aristotle meant in his discussions of physical problems. Ultimately, these mathematicians developed some interesting mathematics out of Aristotle's speculations. The most important result being that a body moving with uniformly accelerating speed traverses in a given time the same distance as a body that in the same time moves with a constant speed equal to the accelerating body's speed at the middle instant. There's a picture, not a very good one. This slide shows a graph of velocity on the vertical axis and time on the horizontal. Distance traveled on the uniform acceleration is the area under the triangle, under the line AEC, above the axis ADB, and distance traveled under constant speed at time D is the area under the line FEG, and you can see easily from the picture that those two are the same. An obvious question here is why, since Aristotle was known both to Muslim and Jewish philosophers, these men never considered the mathematical problems connected with kinematics. But evidently, the ideas of Aristotle were never discussed in a setting in which one could debate these questions. So it was this lack of the ability to debate in a secular setting that helped to prevent both Jews and Muslims from proceeding further in mathematics than they did. One needs to be able to speak with and debate with colleagues to push the ideas further. Okay, so let me just review a little bit. There were clearly mathematical geniuses in all three of these medieval mathematical cultures, most of whom shared a common mathematical background of Hindu-Arabic number system, the works of Aristotle, and Euclid's Elements. Yet starting with the same basic information, the mathematicians from the three cultures were interested in different mathematics. Algebra, of course, had been developed in Eastern Islam, but it seems that the only algebra work available in Western Islam was that of Al-Khwarizmi from the 9th century. Okay, but as we have seen, there was a definite interest in theoretical and practical geometry, and Muslims also advanced the study of trigonometry and worked in combinatorics. As I said, the Jews were not interested in algebra at all. On the other hand, Jewish scholars were very interested in theoretical and practical geometry. There were quite a few authors who investigated advanced geometric topics and were careful to give strict Euclidean proofs. And even Levi ben Gershon in his work in number theory gave strictly Euclidean proofs based on Euclid's own work in number theory. As I said, there was work in combinatorics, and there was a lot of Jewish work in trigonometry. The Catholics themselves had little interest in advanced geometry and did little new in trigonometry, but they understood algebra, but they missed out on Islamic advances beyond Al-Khwarizmi, basically. Al-Khwarizmi's work was translated several times into Latin, in fact, but the advanced algebra that was done in Islam never made it into Catholic Europe during the Middle Ages. Catholics did not understand combinatorics at all. There are some, until what I mentioned, the work of Mersenne much later. But they did develop, as we saw, the mathematics of motion. All right, I want to conclude. Well, I just want to mention briefly, we've said this already, but the Jews and Muslims learned from each other in Spain. Jews and Catholics learned from each other in Provence and in Italy. And Catholics learned much from translations of the Islamic work made from Arabic, often with the assistance of the Jews. But I want to just go back to our man buying a horse problem. As I said, it showed up many times. These are just a few. It shows up in a work of Al-Karaji in Baghdad around 1000 as an abstract problem, not as a work of horses, but as an abstract algebra problem, and it was solved using algebra. Muslims were fluent in algebra, as we said. The horse problem occurs, as I wrote it, in the work of Ibn al-Bana in Morocco in 1300, around 1300. And he also solved it algebraically. It also shows up in Fibonacci's Liber Abaci in 1202 in Italy. But Fibonacci does not use algebra to solve it. He basically uses arithmetic. It shows up abstractly in a work of Jordanus de Namora in Paris, maybe 50 years later. And there it's solved using algebra, although it's a little complicated algebra that Jordanus uses. It shows up in Levi ben Gershon's work. Again, it's an abstract problem. And Levi's solution is sort of strange. He writes this not with the 1/4 and 1/5 and 1/3 that I mentioned before, but sort of any fractions. And he gives a recipe for an answer that you can plug in any numbers you need. But he doesn't show, and he shows that it's correct, but he doesn't show how he got it. But then it does show up in a later work in Constantinople. This is already in 1500. This is a work by Elijah Mizrahi. And it's not a problem about men and a horse. It's a problem about men sharing a fish. Maybe Jews didn't buy horses together, but they did buy fish. And again, Elijah solves it using an arithmetic method. Okay, so thus we can see in this study of mathematics in the medieval period, as in other times and places, that mathematics is not, as people have often asserted, and it really can't be a culture-free subject. It really depends on where and when you live and what is going on around you. I want to thank you for listening, for choosing to learn more about the history of mathematics and how it connects to everything. I want to thank my wife, Phyllis, for her help in designing the presentation and providing feedback. And if you have any questions, I mean, I'll take questions now, obviously, but if you have any others, you can send me an email and I'll try to answer them. Okay. I think I'll.
So thank you so much, Dr. Katz, for giving us this rich cultural and historical context for our thinking about mathematics and religion and their intersection. And like our last two talks, you made deep connections to Jewish and Christian sources, and we really appreciate your further broadening our series by adding perspectives from Islamic sources as well. So we now move into the evening's Q&A portion. I've been collecting some questions from the audience in the chat window, and you're welcome to continue entering additional questions as well, and we'll work those in. Also at this time, Rabbi Zeidman will paste a link into the chat window for the 2-minute anonymous Google Forms survey we'd like each attendee to complete to give us valuable feedback about this session of our speaker series. this session was different from the first two because, again, we focused on math history more this time. By the way, our October 17th talk is also by math historians, Snezana Lawrence, and so you'll get another taste of this style as well. So I guess our first question comes from Jeff Powers, and he asks, you mentioned, Dr. Katz, that things like asymptotes were beyond imagination, and you showed a graph of the conchoid of Nicomedes. How did mathematicians discuss such things so long before analytical geometry people like Fermat and Descartes?
Well, the conchoid of Nicomedes was, I mean, it was described, I can't give you the exact definition right now, but it's a combination of two movements of two points moving and keeping a certain distance between them. And for a hyperbola that we saw on the other slide, I mean, that's described originally as a slice of a cone. Apollonius, in his conic sections that was written, I don't know, in the 3rd century BCE, was able to prove all sorts of results about these kinds of things without any analytic geometry. I don't think they weren't so interested in the distance. The point was that these two lines, these two curves, if you want, just as you trace them further and further, they got closer and closer together without meeting. I mean, they didn't try to put any numerical values on this, but that's what it was. They could draw pictures of them. I mean, we don't have any original picture. I mean, we have pictures from Apollonius's manuscripts, but they were all written in modern times, really. We don't have manuscripts with pictures from long ago, but people talked about these things. And evidently Maimonides was quite fascinated with this idea that you could have two lines that started a given distance apart and got closer and closer together without ever meeting.
Okay. And Jeff has a follow-up question. Does the men buying a horse problem lead to a Diophantine equation? And if so, were medieval mathematicians familiar with Diophantus's work?
Diophantus's work was available in Islam at some point in the Middle Ages. It wasn't available in Europe in the Middle Ages. It was available a little bit later. Yeah, it's four equations and three. No, excuse me. It's 3 equations and 4. Was it? Yeah, and 4 unknowns. And I mean, it's not you don't get a single solution. You need to pick a number for something and so you can simplify, and so you can get it into an equation that gives you an answer. And most of the time, people are only interested in finding one solution.
Okay. We have a question from Gerald Williams.
Wait, excuse me.
Yeah, go ahead.
They didn't think of it as a Diophantine equation in the sense of being solvable only in integers, if that's what you mean by a Diophantine equation. I mean, Diophantus didn't either, but I mean, it was solved in fractions. Often, I mean, I've seen some solutions where the initial solution was in fractions, but then they didn't like that solution. So what you did was multiply everything by the common denominator and get integer solutions.
Okay. Our next question is from Gerald Williams. He asks, given that many adherents to Judaism lived in the same locations as those who practice Catholicism, is there a bound on where you can say Jews weren't interested in algebra?
I'm not sure a bound. I mean, there's the earliest Hebrew work in algebra is probably the 1400s, really. I mean, there weren't any Hebrew works in algebra. I mean, it's clear that Jews didn't study algebra. Yeah, they lived in some of the same areas, but that was just not done. maybe for the reason that Maimonides suggested.
Okay. From Daniel Otero, we have the question, Italian merchants valued the computational processes that describe the exchange of money and maturity of loans at interest, despite restrictions on charging interest. These were absorbed from mathematicians who were both Muslims and Jews, correct?
Yes, I'm sure that's true.
Okay. And from Shariari, who supported mathematicians? In particular, how much did the courts that were interested in supporting mathematicians and scientists discriminate based on faith? Were there courts other than in Spain where scientists of different faiths were supported and collaborated?
Well, I don't know if I can give you a complete answer. I mean, certainly in Europe, when there was mathematicians were supported through universities, maybe, or through contact with rulers. I mean, you remember Galileo or others, but no, I don't think they've supported anybody else other than Catholics. I don't think Jews were not supported in Christian Europe by rulers to do mathematics, as far as I know. I mean, in Spain, if you wanted to do mathematics, you had to get some support from somewhere. Some rulers supported you, and in fact, there is a well-known Islamic mathematician from Spain who, in fact, was a ruler. He became king of one of those small Islamic states at some point, and so he supported himself pretty well. But Abraham Barchia himself had some position in a Muslim state at the time, a Muslim kingdom. So he did have some support, I guess. I mean, it wasn't support for the mathematics; it was support for the rest of his life. But I don't think that happened in Catholic Europe particularly.
Mm-hmm. So here's a couple of bigger picture questions. So math and history are each sometimes stereotyped by the general public as irrelevant rote knowledge that they don't use. And so by focusing on math history, have you gained some insights into how best to help students appreciate how both realms can be taught with relevance, creativity, and a focus on big overarching ideas?
Absolutely. I mean, that's really what I've done in much of my career, is to see how you can use historical ideas in mathematics to teach mathematics. And a lot of people on this Zoom have done the same thing. But to do that, people need to be familiar with the history. I mean, you need to understand both the history and some of the mathematics. And the mathematics often, as we've seen here, comes out of solving problems that were necessary in a particular time and place. So the students need to see, what was going on in that time and that place, and why you needed to solve certain kinds of problems.
So that kind of inspires a question that could be a follow-up for you, but also bringing in Rabbi Zeidman for any thoughts he has. And that is there a parallel in how learning the history of math helps math become more alive and vibrant for math students, and how learning things about the Talmud and its rabbis and their history help Jews maybe make more personal connections to their Judaism? Any thoughts from either of you?
I mean, yes, on the mathematics side, for sure. I mean, that was my experience over the years. And as I've said, a lot of other people on this Zoom have had that same experience. So maybe some of them would want to speak to that, but for sure, it helps to humanize the subject. I mean, often mathematics has been taught as if it were handed down on stone tablets from somewhere, and you just got to go memorize the quadratic formula. Now, I mean, I made this point about quadratic equations, that I mean, yes, quadratic equations are in fact useful in various places there, but it is very difficult at the 9th grade level to figure out problems that students can understand where you actually need quadratic equations. So sometimes students need to have faith that if they learn this, they will actually be able to use this material later on when they know a lot more.
Rabbi Zeidman, did you want to add anything?
I think it's somewhat different depending on how Talmud is being taught, and whether there's a historical sense to the teaching of the Talmud or whether there isn't. But in general, I would agree that there's a humanizing factor when you study the work of history, the work of the past, and reflect on how they came to solutions that were appropriate for the time and the place, through dialogue and discussion and learning from one another and building upon the past to anticipate to prepare for the present and anticipate the future. So it's a very complex thing, but I think, yes, in general, it does, in my view, of course, maybe I'm biased as a rabbi, but yeah, the study of the past should inform the present and inspire us into the future. And one of the reasons why I was so excited for this particular talk was, as somebody who's not particularly mathematically inclined, understanding more about the history of mathematics helps me to have better appreciate and understand the beauty of it.
Thank you. So Dr. Katz, I know you and I have talked a little bit before about, the whole point of this speaker series is to show how math and religion can be more in harmony than people realize. And yet at many private religious day schools, math is taught completely separate from like the Judaics classes, right? And you and I have talked a little bit about, the value of being able to integrate that more. Do you have any thoughts to offer about how best to encourage more of this happening?
Well, I don't know. I mean, it's hard for me to go into a detail, about what you should teach, at a Jewish day school. But in general, it is nice for Jewish students to learn that Jews were involved in mathematics a long time ago. That's one point. I mentioned that Levi Ben Gershon's work is the first place where there's a use of, in a very concerted way, of the principle of mathematical induction. Mathematical induction is something that's usually taught in high school, probably in the junior or senior year, and one could see that it was used, how it was used, where it comes from. But there are a lot of subjects that benefit greatly from history. Trigonometry is interesting. I mean, again, Levi Ben Gershon wrote a textbook on trigonometry. That's really one of the earliest places that I've seen the law of sines, the plane law of sines, not the spherical one, but the plane law of sines. You might want to look at that. It's something that's, why do you need that? Why do you need to study trigonometry at all? Trigonometry has a very important historical basis. It's central to the study of astronomy. Astronomy is important for all sorts of religious purposes, both in Judaism and elsewhere.
Yeah. Rabbi Zeidman, you have something to add?
Just to say that I think that Dr. Katz has made an incredible and an articulate argument this evening for why, if you really want to understand the world and creation and Torah and Talmud and Bible and religious things in broad strokes, generally, not just within Judaism, you really have to understand things about the world, like mathematics and science. If you really want to understand what it is that we're being taught and what Talmud teaches and what religious tracts, Jewish, Muslim, Christian teach, much less how to live in this world with in a way that honors God. You have to, the more you can understand the world, the more you can do the work in it to make the world better and more whole and more complete, and to live a meaningful and successful and hopefully blessed life. So I think, Dr. Katz, you spoke, so you showed us many different ways and many different people who have articulated that. And it's blending mathematics specifically, but quote unquote secular studies with religious studies is clearly not something new. It is very, very, very old, and we've learned that this evening.
There was a question earlier from David Bukowski. How many clergy mathematicians did you encounter in your research? People who are both.
Well, many of these people were. I mean, Levi Ben Gershon himself was certainly a rabbi. I mean, he was a biblical commentator. Most, if you ask most rabbis if they know anything about Levi Ben Gershon, they'll say sure, but they don't know much about his mathematics, but they know about his biblical studies. In Europe, I mean, the people that taught in Catholic universities were generally clergy. That's how you, I mean, that was your career path. I mentioned Marin Mersenne. I mean, he's a bit later, but he was a priest, and he was very important in mathematics in the 16th century. And now I don't know so much about the Muslim ones about being clerics. As far as I know, the people that I talked about were not clerics as such, but so that may be different in Muslims, but among the Muslims. But I think a lot of Jews who studied, when you studied as a young Jew, you learned Torah and Talmud, and so you often just became a rabbi. I mean, that's what you did. And you did other things too. Levi did his mathematics as a side occupation, I guess. I don't know.
Yeah.
I wish we knew more about his life. We really don't know very much about it.
Mm-hmm. There's been some really fascinating things in the chat. This isn't really a question, but I'll just share it. It's just fascinating. Someone says, I was a mathematics professor before attending seminary, and there were many times during seminary when I reached for my mathematics books to help with seminary assignments. Boy, I'd love to hear more about that. That's fascinating. Let me also tell everyone that Rabbi Zeidman has once again posted in the chat window the link to the 2-minute anonymous Google form survey. If you haven't already done that, it'd be great to make sure you remember to do that before you sign out or leave. And also in the chat window is the link to sign up for all 3 of the remaining talks of our 6-speaker series. So, okay, so you can copy and paste the link into a browser and get there. Okay, so anyway, so while you're thinking of it, make sure you've signed up for the remaining 3 talks. They're going to be equally fascinating in yet additional ways. Again, they're all free. Also be aware that all of the talks will get recorded and archived and posted on the Temple Mount Sinai YouTube channel. So if you came late or had to leave early, you'll be able to catch what you missed. Any closing words or thoughts for us, Dr. Katz?
Well, I'm glad that there were so many people that were interested in this subject. I'm pleased that a lot of people showed up. I hope, and a lot of my friends on here. I mean, I know a lot of these people from various places. I'm glad they came. Otherwise, I don't know. I want to thank everybody for coming.
Yes, we absolutely thank everyone for coming. We had a very nice turnout tonight. Rabbi Zeidman, any closing thoughts from you?
Just also an expression of gratitude. Thank you, Dr. Katz. Thank you, Dr. Lesser. Thank you to Sinai and Synapses and the Scientists in Synagogues program. Thank you to the John Templeton Foundation. Thank you all across the board to everyone who's taken an interest. It's so important that we make an effort to counter this misconception that religion and scientific thought and mathematics are at odds inherently. That is not the case. They feed one another. We grow as more whole human beings, the more we know about the world and the more we know about ourselves and our purpose in it. And I'm grateful to be a part of knocking down some of those perceived barriers and to make this conversation more accessible on both sides. Whether you're somebody who comes to this conversation because you're interested in mathematics, or you come to this conversation because you're interested in religion and religious traditions. So grateful to everyone for taking the time this evening and for doing a little learning with us. We're grateful. And again, thank you, Dr. Katz. Thank you, Dr. Lesser.
Well, thank you again for inviting me, and I will sign in for the other 3 talks as well.
You have been a regular attendee, and we appreciate that too. Thank you.
Yeah.
Well, we're excited to be welcoming in August Dr. Olga Koshaleva and Dr. Vlada Krajinovic. And please do sign up for our next topic conversation. And hoping everybody is safe and healthy and has a nice couple of months until we see you again.